You see my screen?
Good day, yes.
So I apologize that we have two lectures. So I would like to that we will compensate it. So if you will have a possibility on the next week for some day, even to provide one lecture, so please tell me, we can, because I would like to give to reach at least to reach the point which is important in cosmology up to inflation stage and like this. So, for example, Wednesday it's okay for me on the next week. Of course, Monday it will be as usual, but we are working up to 8 December, as I understand. Yes. And tomorrow we also have a lecture, yes?
Yeah, tomorrow we have.
Tomorrow we have. Let's see. Yes, we have.
Yes, tomorrow we have.
Okay. Okay, let's see. Now we will start. So we finished. Let me see. What is this? Okay. So we are working with a multi-component model of universe, and we estimated. Yes, what is important that we understood that we can divide the evolution of the universe on 3 stages, just looking on the solution of Friedman Lemaitre equation. So this is radiation error. I look here. Okay. This is radiation error. This is predominance of matter, and this is the error of when the lambda term is much more important and give much more influence contribution in the total energy density. So we also estimated, we need to understand which component of the universe, for example, for now is important. So we looked on the relative density of radiation, so this one, and the conclusion which we could make that when we estimated that when we speak about radiation, it means that this is emission of all stars during all time of universe existence. This is the first, so we need to put here plus omega stars 0. And we discovered it's really small, so it's not a point to take into account this. This is microwave background, cosmic microwave background, and we discovered that it's really important contribution due to the fact that these photons are distributed homogeneous in all space. So the point why this is not so huge number, because as we discovered before and we discussed it before, because the structure of the universe looks like a net. So, and the distribution of galaxies together with the stars inside looks like a spider net, and it's located in filaments. So, and we have a huge void where we don't have any stars and galaxies. And due to this, if we calculate the emission of all stars, it will be not so important. It will not give a lot of contribution with the total energy density of the radiation in comparison to CMB and also neutrino. So this is final number which we have for relative density, energy density. We also need to understand what else we have. And the next point is, since I will write here, okay, remind that the total relative energy, the total relative energy density, omega 0 for the present time. Again, when I put 0, it means that we speak about present time. So this the sum of omega radiation on the present time. We need also to put omega matter on the present time. And God knows we need to put also omega lambda, which is a constant, but just a put. It's not important even to 0 equals 0. Good. So not important to put 0 because as we discovered, it's a constant. So now let's speak about matter. And omega matter 0, this is relative energy density at present time, energy density of matter. So what means matter? This omega m0 consists of two components. So the first component is, and can usually it's using the index like this. So I will put index B, which that means baryonic matter. So for the present time, plus omega C dm on the present time. Okay, yeah. So baryonic matter. So let's baryonic, and this is called dark matter. What means baryonic? So it means that we speak about principle all matter which we can observe and which can connect with electromagnetic emission. So of course, as I already said before, so baryons, it means protons and neutrons. So of course, we can speak about leptons, which is, for example, electrons. But again, since so plus leptons, but the mass of leptons is much less than the mass of baryons, so it's not a point to speak about this. But of course, we need to take into account. So usually we just speak, which we would like to say about just normal matter. We speak about baryonic matter. This is everything what we can see. So this is Earth, this is planets, stars, galaxies, gas also, gas in cluster of galaxies, so everything. It means that when I say that what we can see, it means that this matter can interact with electromagnetic emission. So in any band. So this matter also can be the source of the emission. About cold dark matter, in principle, of course, it's not important to say exactly cold. In a much more general case, we can speak about warm or hot dark matter. Again, I already said before that in standard cosmological model about which we speak, we suggest, and it looks like the dark matter should be cold, and sense that dark matter consists of the particles with a large mass, even larger than mass of protons. So why we speak about cold? So this kind of estimation of the temperature of dark matter tell us about the mass of these particles. To estimate the influence and the relative density of cold dark matter, it's taken from different way. It's a direct, you know, it's complicated to do something direct in astrophysics and cosmology, but in any case, this is investigation of rotation curves in the galaxies, which tells that the rotation curve is not Keplerian, so we can feel that should be some additional mass. It's also investigation of cosmic microwave background, which can tell also the information about cold dark matter mass. I just want to show you, for example, okay. So, you know, what is important, this is to look the right sites where you can find the right information about cosmology and astrophysics, principle and information. So this is, for example, the site, the link on the satellite Planck. This is European Space Agency, because it's exactly European Space Agency was responsible for the launch and working of Planck satellite, which called Planck. Here you can see such a kind of, sometimes we, as a joke, say that this is cosmological cake. So, and even you can see the representation of the two cases. So the distribution, or how call it, the components of the universe before launch of the Planck, like launch of this satellite Planck telescope, space telescope. Here you can see that dark matter, it's 22.7% before Planck, and ordinary matter 4.5. For after Planck, so when Planck gave much more precise result for estimation of dark matter and ordinary matter, which we call baryonic matter, so you can see that it's a little bit changed, a little bit from the point of baryonic matter and dark matter, especially for baryonic matter. So baryonic matter, this is 4.9%, and dark matter 26.8%. What is interesting, and about dark energy, so it's understandable about dark energy, because look, let's come back here. About dark energy, we can immediately to understand, so since omega 0 equal unity for the flat space, remember that we discovered that it can be three possibility of the curvature of the space if we have a homogeneous and isotropy of the universe, and flat space correspond when omega 0 equal unity. So, and this point, this is also observational discovery. The omega zero equal units come from CMB, so if you will have time, we will speak about this. And since from the right side we have 1, so we can understand that if we would like to find the omega lambda, it means that it should be 1 minus omega r0 minus omega m0. So this is the point. If you estimate this one and this one, finally you can obtain the value of omega lambda. Of course, you can say, okay, but I'm sure that we really have this component. Maybe we just need to erase it from this quality. But again, we know that now universe expand with acceleration, and this exactly tells that we need to involve, we need to put in our equations this lambda term, which is exactly responsible, as we could see before, for the acceleration of the space. So, and as soon as we already used it, we put it as an explanation of acceleration of the universe. It means that we can estimate it like this. So this is such a point. Let's come back here. So what is interesting in this this cake? Also, we can look. We can write another above the map. Okay. NASA. Okay. Go to NASA. So this is another satellite which also discovered the cosmic microwave background. So you can see here, the W team received the Cosmological Prize Gruber, and also Kobe received the Nobel Prize. Let's go here. So you can, for example, go to this page. This is National Aeronautics and Space Administration, so which you know well, maybe this NASA, 4 letters. And NASA was responsible exactly for this satellite. And I don't know, maybe I can look on the cake, cosmological cake here, because it was before Planck. By the way, you can see this picture, Einstein, and now you already can recognize the Einstein equation here for the empty space. Okay. Our universe maybe here. Oh, I don't know. They maybe didn't put here the cake. And before Planck satellite was a double VMAP satellite, the double VMAP space telescope to investigate cosmic microwave background. And before double VMAP, it was Kobe. Okay. Okay. Kobe mission. So this is another satellite. This is NASA. NASA Golf. Okay, here. So before it was another satellite, Kobe, which is the first obtain information about cosmic microwave background, and discovered anisotropy of this CMB, which can tell us about the history of the universe, and the universe was really very young. We will see, we will obtain this time when this cosmic microwave background became free, and we will understand from which time we receive the information about universe. So just, you know, to, for example, for you to look later after lecture these pages, and for this discovery, it was given the Nobel Prize. So, for example, Kobe Nobel Prize. Yes, 2006. So John Mather and George Smoot, and you can see here that they received the Nobel Prize to 2006 for their discovery of the black body form and anisotropy of the cosmic microwave background radiation. So if we will have a time, we will speak much more in detail about this. Now let's come back and schematically. Okay. Just, you know, to remember that discovery of CMB let's write CMB. This is the first was a satellite space telescope Hobby. The second W map, the third Planck, and let's put here they are important for important to obtain the information about omega contact matter 0 plus others values. It's understandable that lambda also, you can even as I remember correctly on the I will look later on the page on W map, you can even find the page where you can play with the numbers and to see how will change the spectrum of cosmic microwave background. So, and what is also interesting that you can see also that let's come back here, that the ordinary matter just 5%. So it's really a very small value. So if you will look on the universe from the point of energy density, the ordinary matter, which we can see as galaxies, planets, everything, and including this is just a 5%. So it's really fortunate this ordinary matter exists. And as you can see, much more, whether this is approximately 95%, this dark matter and dark is that the universe is really dark. Of course, dark, sometimes we use this term dark when we also don't understand enough nature of this, so, and we call it dark. But in this case, when we use this term dark, it means that such a kind of matter doesn't participate in production of emission. So, and we really can't see it. We can see it only due to the you know, some fact that something moving, not due to the, for example, due to the exactly Newtonian law in sense that in the galaxy, if we will consider the central mass and we take into account of matter, all matter, ordinary matter inside, and we understand how it should move. But we can see that it's moved something strange way, much more fast, and it tells us that something present. Or, for example, we look on the gravitational lensing effect, and we can see that the galaxy between source and us much mass that we can see in optical band, including other bands. So this is the point. Okay, so we can take this for estimation now conspect, and so let's put here that lambda CDM, cold dark matter, for the present time equal 26.8%. All in percent, it's not good to write. So let's like this 0.26.8. And omega baryonic equal 4.9%. So you can see percent, okay, 0.49. By the way, much more part in this call it English, much more contribution give intergalactic gas. So the gas inside the galaxy cluster of galaxies. If you calculate only stars, it will be the less part. If, for example, we will consider, because the cluster of galaxies, this is like, you know, like galaxies, which are surrounded by gas, which we can see in, for example, X-ray, because this is hot gas. So this is a lot of free electrons, and this is like this. So in this value, we can say that much more introduction,
So
much more.
probably for baryon matter, we need to put 0 before 49.
I see, chair, of course. Yes. Thank you. Yeah, you know, I would like that the ordinary matter will be more than we have. So, okay, and finally, if we will, you can understand that omega lambda 0, it's altogether, okay, matter 0, it will have omega CM, CDM 0 plus omega baryon 0. And so how much we will have? 0, 7, 3, 1, like this. So approximately we can consider 0.3. And omega lambda will be omega 1 minus omega matter 0 to make all budget, you know, is 100% of unity. So it will be approximately 0.7. Or much more precise, so I will put here to tell, and usually when you, for example, you write a paper where you are using, you make some calculations for the object which are really far on cosmological distance from us, you sure need to say about cosmological model which you are using, and also about this constant. So this we took from, now we already precise, and we can Planck. There are two sorry, Planck, see. There are two releases, in 2013 and 2015. So last one's 2015, but doesn't change a lot. What is also interesting that you can see, and this is really incredible, why the Nobel Prize, when it was given for discovery on CMB, for cosmological discovery, and it was also said that also starting from this time, the cosmology became precise science, in sense that we can find, for example, for this case, we can find these parameters up to the third sign under comma. So, and this is really, really very interesting and important. So, okay, and I will put here omega lambda, much more precise value, just, you know, okay, 10%. 6, 3. So this is also Planck. Okay. This is the budget. Now we have everything to obtain some important values, to understand when, for example, we had in the past, or we will have in the future, some important, we'll come back here, some important moment when the universe passes from one stage to another stage. Okay, this one and this one, we would like to understand it. So to do this, it's very simple. So the question, the next question, which we would like to ask, want to find A, we call it, how we call it, RM. So when we pass from the radiation era to matter dominance era, okay? So, and we call it, we want to find this one. Yes. So I'm sorry, I have now my lectures, but we will see. Maybe I will be coffee break. Yes, coffee break. I will succeed. Okay, and T R so the scale factor and the time, cosmological time. T, yes, T we call cosmological time. And also we want to find M lambda. This is the important time when we go from, you know, a matter era, age or stage where the energy density of the matter was important, much more than others, to the dark energy era. So this one. So we want to find AM lambda and TM lambda. So let's find it. In the first, I want to find the ratio between omega m0 divided on omega r0. So, and we have all values. So it's we found 0.3 divided on Okay, 8. Approximately, it will be approximately 3,000 or 3,600. I don't remember this much more precise. I can quickly calculate it. Just okay, so if to be precise, so it will be in any case approximately 700. Okay, so in any case it's approximately 3,000. So and we can see that if we will compare the omega matter with omega radiation, we can see that on the present time omega m much more than omega radiation, which is obviously so we can see even from the value. If we will go in the past, since we remember that omega m equal omega m0 divide on a cube, we found it before, and omega radiation equal, or relativistic matter, equal omega r0 divide on a4. If we will find omega m as a function on a, divide on omega r as a, sorry, it's a function of a. So we will have omega m0 divide on omega r0 multiply on a. Okay, so and if you want to find when they will be equal each other, we need to put here equal unity. Okay, and here I will put Rm. So you can repeat, but I just put like this. And ARM, in this case, just equal, very simple, R0 divide on M0. So this is approximately will be 3 minus 4. So it tells us that this moment when we go from the radiation stage to matter stage was in the past, when the scale factor, which was less as 10 in minus 4th, so it's in 10,000 times the space was stretched. Okay, so and we also can estimate the, for example, the redshift, cosmological redshift, because this is something which we are using in cosmology. If you speak about far object, we would like to use exactly redshift. We already spoke in the beginning about this. Redshift, this related with a scale factor that A0 divide on A equal 1 plus Z. So this is where Z at this redshift, cosmological redshift. It means that I will not repeat it, so we obtained it before in the first lectures. So it means that if you want to find Z, which correspond Rm, we need to end IA0 equal 1 So we need to just to do some simple things. -1, it is not important, just 1 divided on A in this case. And it's again approximately, okay, this, let's put it like this, okay. So this is the redshift on which, and this one, let's put it in some frame. This one, and this one. This is to value when omega r equal omega n. Before to estimate the time, I also in principle we can know the time. We need to solve this some equation. Now I want to find this I can put here for A R M. Now I want to find R. Oh, sorry, M lambda. When we pass from the matter stage to lambda term stage, okay, dark matter. So it's also simple to do. We just and by the anyway we can estimate that omega lambda divided on omega m 0 equal, so omega lambda, okay, 0.7, we use this, divide on 0.3. This is approximately like 2.5 maybe, right? So, and so we can see in any case for the present time, okay, now lambda term, or like this, now omega lambda more than omega m0. So we can see that for the present time, the energy density of the dark matter is larger than energy density of the ordinary matter. So we already understand that we are living in the stage of the dark energy. So, and if we will estimate when it was, again we write that omega, omega lambda is a constant, so we can immediately to write omega m0, which we already know how from this, how this changed. So we will have oh, sorry, I keep omega m. This is constant. This is depend on A. Okay, so and this is omega lambda divided on omega m0 on A cube. And now I want to find when it was equal each other, so I put unity because I want to find that when omega lambda equal omega matter. And here I will write m lambda. So, and from this I can obtain that A m lambda we can find as a ratio omega m0 omega lambda. So approximately approximately it will be how much? 0.7, like this. So if you will take 0.3, divide them to be, yeah, I think like this. Let me see. Of course, 0.4. 0.4. Ah, one is the first, sorry. Yes, approximately 0.775, doesn't matter. Okay. And you can see also, so if, for example, in the future it will be launched the next satellite and some value will be find with much more precise things. So you can immediately to recalculate this. So this formula will continue to work at the point only that you will obtain the another value. And let's consider which.
Sorry, why we have in previous case A in first grade and here in third. So not grade but power.
Where exactly? By the way, if not, in any case, I can see here, I need to put not here, but here I need to put RM. Yes, please ask again. I didn't understand the question.
So here before we have
which line? Tell me which line
from
this. Is the first, the second, third? Which line?
Maybe fourth. So in fourth line we have ARM in first.
No, this is M lambda. This is not this is M lambda. And the first, yes.
Oh no, so that's not okay. So that's not maybe no. This is wrong line. So I mean the line where omega m divided by omega r, and that's equal 1. In this case, we have only ARM. However, in case for M lambda, we have this, and corresponding to this form, to this expression, yes, in first case. So why we have different power?
Because look here, we have omega m, which is a function of scalar factor like this. Okay, omega r is a function of a like this. If you divide this one on this one, you will obtain this one. So you will obtain the first power of a. It's understandable here.
Yes, now it's understandable.
But here you have omega lambda, which is constant. It doesn't depend on a, because it's lambda is a constant. It depends only the cosmological term. But omega m again depends. Look on this. See my pen here. So, and why we have this? Look on I will put here a cube. Because you divide the constant, this one, divide on this one, which is this one.
I understood. I just missed these expressions. Sorry.
Okay, no, so we can also find the the redshift m lambda, which is we need to find 1 divided on a m lambda minus 1. Okay, so 1 divide 0.7 minus 1, it will be approximately like 0.5. If we will remind that, you know, why immediately find the redshift and now speak about this, because it's simple to find. For example, if you want to go from scale factor to cosmological time, it's a little bit much more complicated, because, you know, it's an integral expression. But from here, we can immediately see what is important, that if you will speak about object, usually we speak the redshift as a correspondence to the distance. And when we speak about and time, so, and it's understandable why, when we principle in astrophysics and cosmology, when we look on the object, the stars and galaxy, and principle understands that we look in the past, because the light go to us sometimes to reach us due to the fact that speed of light is constant. And this value is really small, because when we speak about far object, quasars like this, they have or far galaxies, they have the redshift, which is much more than unity. So, and it means that this event, when we pass from radiation era, from matter stage to dark energy stage. Again, when we speak now about dark energy, we consider lambda constant. So, and here we speak passing from radiation stage to matter stage. So let's put it here like this. So it was not so many times ago. Now I want to I would like to find the time which correspond to this, and I think how it's better to do it. Okay. In any case, now I want to consider the situation and to find some expression. Consider the model when matter plus lambda model. So it means that I consider two components which in principle correspond to the stage of the universe, you know, passing from when we need to take into account and matter, ordinary matter density, and also lambda density. So just to find also the expression for the cosmological time. This case, and we when we write Friedmann-Lemaitre equation, we obtained it before. So this is H. I will write it through the Hubble parameter. H divided on H0 square equal. And on the right side, as you remember, we have a components of the universe. So I will keep M0 divided on A cube. This is a matter. Plus And omega lambda 0 doesn't matter, you know, I keep 0, but again, I will remind that omega lambda 0, lambda, this is constant. So if we, again, as you know, I consider k equals 0, otherwise I need to put additional term which is related with the curvature of space. So I'll consider k equals 0. In this case, we can, since we remember that h equal a point divided on a, we can write that so instead to this one, I put a point square divide a square. So h in this case, so I will have like this. H0t equal, I already integrate on the left side from 0 to some t equal, we'll put integral dA, like this, omega m0 divided on a plus omega lambda 0 a square, because I need to move this a square, minus 1 divided on 2. And I want to put it from 0 to a. So if I will integrate it, in the first I want to, this is not important to put 0. So omega lambda, I take out this outside of integral, so, and I will have 0 from 0 to a, dA divide on omega m0 divide omega lambda 1 divided on a plus a square. So this is a table integral, and this table integral bring us to some logarithm. So you can prove it. I will write final expression, and this is, it will be a home task for you to prove it. Oh, so good. Home task. So final expression which we obtain, h0 multiply on t equal, and I will write you just, you know, simple procedure, but in any case it's omega lambda 1 divided on 2. If you will not succeed, so you can a divide am lambda plus square root 1 plus a divide am lambda cube. I don't want to spend time for this. So let's try to obtain at home this expression and send to me. You also will need to take into account that since you can see here that I put am lambda, that omega m0 divide on omega, omega lambda equal a m lambda cube. We obtained it before. So this is why it's important, because this expression gives us So again, home task, I give you, okay, 1 week, but it's, you can immediately to prove it. So this is home task to prove it. As usual, send me an email. This expression allow us to obtain the dependence between t and scale factor for the universe which consists of lambda. So it means that in principle we can estimate the cosmological age, cosmological moment when we pass from the ordinary matter to lambda term. From this we can see that that if we so the early time, so if you go for the time when A was much less than AM lambda, so we can simplify this. So this is 2 divided on approximately 3 omega lambda 1 divided on 2. And since this value is less than unity, so we can consider the series, and it will be just we can put here just A divided on AM lambda in 3 divided on 2. So, and from this we can see that for this time the dependence of scale factor as a function of cosmological time, to be approximately precise, so it's looks like tautology, but in any case, so omega t and I'm lazy to do it. I will write like this. So it will be proportional t in 2 divided on 3. So this is of course for k equal 0. Okay, again we need to remember this. In principle, we can also, it will be useful. So we can write that a cube equal approximately am lambda cube omega lambda 0. Again, 0 is not important. 3 divided on 2 h0t. And since this one, this is omega m0 c above, okay, c from this. We can write more exact, approximate exact expression. It's sorry to say like this, but like 3 divided on 2 h02 t. Omega 0 2 divided on 3. So this is if I didn't do any mistake, this is expression. This is expression between which connect the scale factor and the cosmological time for this condition. Otherwise, or from another case, when we go in future, and so we have a situation when the scale factor is larger than am lambda. So this is lambda term stage. So in this case, we want to find the correspondent with the time. And in this case, we write, so we look on this expression, this one. So, and I can write that H0t equal, okay, on this expression. We look on this expression. Okay. Okay. 2 divided on 3 square root omega lambda. And since since this is big, so we have finally approximately, we need to put it, okay, logarithm 2 a divided on a m lambda. Just write it just to understand what I'm doing. This 2 is not important, so it's not important, we can forget about this. So so approximately like this, so we H0t, this is, and look, 2 divided on 3 disappeared, so this is 1 divided on square root omega lambda logarithm a divided on a m lambda. So this is relation between cosmological time and scale factor. And from this we can see that if we will write the scale factor as a function of t, it will be a m lambda, and since we have a logarithm, we will have e exponent square root omega lambda, it's not important, H0t. So again, we can see, and as in one component model, that in the future the scale factor expand and change exponentially. So, and again, this is k equal 0, as we remember. What is what we can use it, for example, to find now I want to find from this, I want to find the time when we had this path from matter stage to lambda term stage to dark energy. So let's find now t m lambda. So what is it? This is cosmological time, time of matter, dark energy. Let's call it event, okay? Event. Event, it means moment of time, cosmological moment. Moment. Like this. Moment of cosmological time when matter equal dark matter, like this. Okay. I'm now Russian. I would like to find something, to find this TM lambda so, and I need to be careful not to make a mistake. So now we can estimate it. Look, I need to find this moment of time. I need to use this. Let's call it here. I need to look this formula. And in this formula, I need to put A equal A m lambda. Okay, so I can put A equal A m lambda in this. So if I will put it, so what we will have? Okay, left part the same. H0 T, and now I will put index this one because I put this condition. So to divide on 3 square root omega lambda. And look, if I will put here A equal m lambda, so I will have 1 plus square root of 2. So logarithm 1 plus square root of 2. So, you can rewrite. I will use like this. And here I put H0. So you can see that to find this moment of time, it's enough to know as a parameter H0, so Hubble constant, and omega lambda. And omega lambda we can find from investigation of CMB like this. So if you know these two values, you can understand when we had or we will have this moment of time, but it was in the past. We already understood it. So let's put the numbers. And estimated Tm lambda equal, and just put it 2 divide on 3 square root
0.7.
here 1.7. Yes, square root, yes. I didn't do it. It's square root of omega lambda. It's right. Just started to say no, everything is correct. Okay, multiply on 0.7. Let's consider approximately. Okay. Yes. And this number. Here we need to be careful because we H0 it's not good to write like this. In the first, I will put here H0, and after this, we need to understand what is H. So H0. If this is like approximately 70 kilometer per second divided on megaparsec, we understand that this is H0, this is the dimension, this is 1 divided on time. So, and of course you need to, and we maybe did it before, to consider this in the dimension of the second, 1 divided on second. Otherwise, if we will put it like this, it will be not like just a 70. So I just can, it should be 2 multiply 8 minus 18 seconds. So if you will put it here, we will obtain, you can do your calculations now freely because you have all formulas which we can use. It's just the point, and you have also the number of parameters, and you understand where you can find them. So I just, the idea to show you how you can calculate it. And finally, we can obtain that m lambda, I just know this by heart, it's approximately 9 billion, this is a 9, yes? Billion years. So it means that when we speak about cosmological time go from the birth of the universe to the present time. It means that approximately we can write as a conclusion to this point. Conclusion. So that 9 billions years after. I hate this, I don't like this Big Bang, but after Big Bang, it was an event, was a moment of time. You can write by event, so I used to write it. It was the universe, or universe, passed from matter-dominated ages to dark energy dominate stage. So, and it was just approximately 4 billion years far from present time. So 4 billions years from in past from present time. So it was really not long time ago. Can you think this is just 4 billion years? It's not a lot of time. If we consider this is the time which we compare with the scale of existence of the sun, of period of the sun, Earth, and like this. So it's really amazing because and what is important. So I would like to say that, and this is very important event in the universe, because starting from this 4 billion years ago, the universe start expand with acceleration, and dark matter finally won the ordinary matter. So, and starting from this time, you can write. We have acceleration of the space due to lambda-torn, due to dark energy. And here I have 1 minute, so I can finalize this lecture with a philosophical point, because it's really fortuna in Italiano, that it was, for example, 4 billion years ago. Why? Because up to already on this time, the large scale of the universe was formed, and also was formed the galaxy, group of galaxy like this. So the general structure of the universe was already ready in the sense that what we can see now. If, for example, the dark energy could switch on earlier, not, for example, 4 billion years ago, but like much earlier, when it was important to construct, when it was important, when the first structures was formed, this dark energy could expand the space and to prevent the gravitational collapse of the matter, to create the first seeds for the formation later galaxies and like this. So this is because this is concur between competition between gravitational forces, which which try to compress matter to create a gravitational object, with a competition with energy forces, dark energy forces, which try to otherwise to stretch everything. And it was very important that on the time of formation of large scale of the universe and the first galaxies, stars, and like this, and cluster of galaxies. So the lambda term was not didn't have so much contribution. And sometimes it's even was discussed like the second anthropic principle. So it looks like, the universe such a way that finally the observer will appear like a human being, who can observe this universe. And this looks like, it's a really fortune that we are living in the universe where the law such a way that the dark energy started to be very important and the dynamics of the universe only 4 billion years ago, but not earlier. So this is the end of the lecture. If you have a question, please ask me. I will make now snapshot. No, screenshot. Snapshot I'm doing for body simulation. And this is screenshot. Okay.
I just want to say that we have lecture only until 6 December, until Wednesday, because on Friday we have first exam.
Okay, up to 6. Okay. It's a pity because so we want to say that we have only 2 lectures.
Yes, no, we can spend lecture in any time, no, just until Wednesday.
Okay, I will try to succeed with very quickly to speak about inflation stage of the universe and something else, but I need additional 1 lecture. I will try to collect all things in 3 lectures. So I need some additional day. If you are agree about Wednesday, so it will be okay. 6.
Okay, we have 3 short lecture and 5 lecture.
We can if you agree, because in any case I will put a question about inflation stage and like this, and this is really interesting because this is one of the. So if you agree to put so the second and the fourth we have lectures, and we can, for example, to find for the 6th I can give 2 lectures. Final lectures, if you agree, and it will be 4 lectures, 1, 2, 3, 5 lectures finally. What do you think?
I agree.
What about others?
So maybe we should make it not on Wednesday.
Yes,
maybe
on
on
Wednesday,
Tuesday.
for example, we can make 2 lectures, if you agree. Final lectures.
And what lectures it would be?
At which time, or you want to
Yes,
know?
Which time?
This is when it's comfortable for you. Tell me the time, because Wednesday I can provide exactly for your time. When any time for me is okay. So let's think and write me. Maybe you need to discuss and write me in Telegram channel. Okay.
Okay.
Fine. So, and just to say that what I plan quickly, not quickly, but what I would like to finalize. So, what is important from my point view? So, it's a pity that I missed 2 lectures, but this is life. So, this is to calculate the time of the passing from radiation to matter, and maybe immediately we will speak about the problem of this Friedman cosmology, which is important, and after this we will justify and we will understand that we need to create something additional, and this is inflation stage of the universe. So we will speak about time when the universe started to evolve from a quantum state to the macro scale, taking into account the points that we need to explain the scale structure of the universe, to explain why the universe, the space in the universe is flat, the curvature is equal, and like this. And also, I would like to speak a little about CMB and dark matter, so hot stage of the universe. I will try to do it during 5 lectures. If you agree with this, so we will really succeed. Okay, so I wait from you the message in Telegram channel. Please send me your calculations for the last home task. I will take into account for all of them for estimation of your knowledge exam. Do you have some additional questions?
I'm sorry. Could you repeat home task, please? And
Task, home task. This is to obtain this expression from this one. Taken into account this one. Stupid things? Not stupid. In principle, you need to do some procedure. Okay.
thank you. Thank you.
But it's, you know, to work a little bit with this. Some additional questions? No questions? Okay, in this case, let's say in Italian, buon giornata, and see you tomorrow.
See you tomorrow. Thanks for watching. Bye.
Thank you.